Okay, so it's my pleasure to introduce Professor Ignas Snellen, who works at the University of Leiden. He did his PhD in Leiden, but then came to the here at the IoA in Cambridge. Well, here is a big word. After that, he went to Scotland to be a lecturer at the University of Edinburgh, and then circled nicely back to Leiden, where he's been a professor since 2004, I think. He's an expert in exoplanets, and he mainly works well, his title says it all, exoplanets and the search for extraterrestrial life. And I'm very excited to hear his talk. Yes, all yours.
Thank you very much. Let me share my screen. I've done this now 1,000 times in the last half year, so that should probably work. Like this. Right, can you all hear me? So yeah, very nice that you're all listening in, and thank you for asking me. So my talk is on exoplanets and the search for life. Now, of course, a real issue with these online talks is that it's so difficult to interact, but please try to actually do so. So if you have a question or comment, or I'm not sure whether that's actually allowed here, but just shout actually out or something to try to actually stop me. So yeah, when you work in this field for a while, you sometimes forget that only 3 decades ago, the only planets that we knew were those in our own solar system. Yeah, and then everything changed with when 51 Pexus b was found, which was the onset of a real revolution. Now, a few years later, the first transit was measured, the first atmosphere, thermal emission, moving away from hot Jupiters. Exo-Neptunes were found, the first direct image, molecules, atmospheric dynamics, planet spin. And in the meantime, finding thousands of planets down to the first exo-Earths, planets with a mass and size like Earth, which also could have similar climates, and liquid water on the surface. Of course, I mean here Proxima b and the actual TRAPPIST-1 planets. Now, this revolution is here mainly because our instruments are getting much better. For example, the accuracy of radial velocity measurements has since the 1980s increased by a factor of 1,000 or so. Now, and in this way, we can peer into the future. Now, we have these great observatories are coming online, James Webb and the ELTs, which is very exciting. We can start probing the atmospheres of mini Neptunes and super Earths, and even some Earth-like planets around nearby M-dwarfs. Possibly even probing biomarker gases. So in this talk, I will broadly show you where we are now and how we want to actually do this in the future. But maybe it's good to first discuss why we are all doing this. I often have to explain this if I give a public talk. I get comments like, who cares about other Earth many light years away, we can never go there anyway. Well, I think this is not about distant worlds per se, right? This is about ourselves. We want, what are we actually doing here? About understanding the place and role of the Earth and the solar system in the universe. This has, of course, a very strong philosophical aspect. You know, we can ask existential questions about humanity and life on Earth. How do planets form? How does the solar system fit in? Is it in any way special? And if so, why? And then, of course, the 100 billion euro question: are we alone? Does life exist elsewhere? I think it can really change the way that we see ourselves, like Galileo's work did 500 years ago, like Darwin did. And for example, at some extent, the first Apollo photos of the Earth as a whole. Now, evidence for extraterrestrial life will really sharpen the view of ourselves further. Now, okay, before we go to the exoplanets, there are of course planets that we know very well, those in our own solar system. Now, what do we very broadly speaking learn from them? Well, clearly, planets are very complex and diverse systems, much more than, for example, stars are, which you can mostly describe using only a few parameters. This is not the case for planets. You only have to look at these rocky planets and moons with atmospheres, Venus, Earth, Mars, and Titan. They are so different. Venus has a very thick sulfuric acid clouds in a CO2-based atmosphere. The Earth is nitrogen-based, but partially clear with water clouds and a large fraction of biotic oxygen. And Mars' atmosphere, again, is very thin, CO2 based again, and then Titan has again a thick nitrogen based atmosphere with opaque methane and ethane clouds. How are we ever going to make any sense out of this mess? Well, I like to compare that with one of my all-time heroes. I already mentioned him briefly, Charles Darwin. What if Darwin only knew about 3 species, an owl, a monkey, and a scorpion? Of course, he would never be able to come up with his great theory about the tree of life. He had to go on this epic journey aboard the Beagle, along the shores and coasts of distant islands to actually see what is actually out there. I see our exoplanet endeavor also a bit in this way, as a kind of an epic journey. It's going to be really hard and really difficult, but I think the only way in the end to begin to see possible families and orders or classes of planets and understand their formation and evolutionary relationships. So where are we now after 25 years of exoplanet research? Now, we found more than 4,000 planets. And the diversity is even larger than in our own solar system. All these types of planets which we did not know could actually exist, like the hot Jupiters. Now, gas giant planets in very short orbits, not clear how they are formed. Super Jupiters, very massive gas giants at very large orbital distances, often up to hundreds of AU out. How do they actually get there? And then there is this very diverse class of mini Neptunes and super Earths, very common in the Milky Way, but not in our own solar system. About 1 in 10 stars host a Jupiter-mass planet. About 1 in 5 stars a Neptune, and most stars probably have Earth-mass planets. So these are really common. Now, this has resulted in a very important recent milestone, although it's not so recent anymore. But as we all know, the actual discovery of Proxima Cen b, an Earth-mass planet around our nearest neighbor. Now, actually, although it's only in an 11-day orbit, Proxima itself is actually so weak compared to the Sun that the planet receives starlight at the level a planet would have in an orbit between that of the Earth and Mars. It could well have liquid water on its surface. Now, another fascinating system is, of course, the TRAPPIST-1 system with 7 sister Earth planets, of which 3 or more could have such climate that liquid water can exist on the surface. Now, finding true Earth analogs, so we're talking here about Earth-mass planets in an Earth orbit around Sun-like stars, are still out of the realm what is currently possible and need a new type of survey to actually find them. Now, we with the HARPS-3 group, we built HARPS-3 for the terra hunting experiment. This is led by Didier. This has exactly this as the aim. Now, with HARPS on the Isaac Newton telescope, or a copy of HARPS, we will survey about 50 stars every night for a decade, expecting to actually bring us to the realm of the true Earth analogs. Now, when we want to characterize planets, what are the global properties that we want to find out? What questions can we ask? Well, first of all, now what is the bulk composition of a planet? Now, does it have an atmosphere or not? What is its chemical makeup? What is its climate like? How hot or how warm is it there? And what difference between the day and night side? Can we link these properties with the formation and evolution of the planet? And do we then really understand all the physical and chemical processes that happen in these atmospheres? And are they possibly in some way linked to any geological processes of a planet? And if we then zoom in on more Earth-like planets, then we can ask to what extent the planet has water, has possibly any biosignature gases, such as oxygen, ozone, or methane. And then possibly the most difficult question of all, are these biomarker gases really due to biological activity or not? Now, of course, for molecular oxygen and ozone on Earth, this is indeed the case. But theorists have already identified several other processes in rocky planet atmospheres that could also lead to oxygen buildup. For example, by the evaporation of a significant ocean, where the hydrogen atoms from water ultimately escape to space, leaving the oxygen actually behind. Now, luckily, the same models show that these different scenarios can be identified by the presence or not of other molecular species, such as CO, CO2, or methane. Now, talking about biomarker gases, it's maybe good to take one step back for a moment and go back to Venus. I want to briefly mention the phosphine story because I had a small role in that as well. You're probably aware of this story very well. It's hard to miss. In September, Jane Greaves and her team announced a detection of phosphine with ALMA in the atmosphere of Venus without phosphine having an identifiable chemical pathway or production through geological or atmospheric processes. Now, since phosphine is produced by some bacteria on Earth, it could be an indication of life. Now, the story had very quickly quite a sharp turn. Already a few weeks later, we showed that the 15 sigma detection is not at all 15 sigma, but it's only about 2 sigma. And it only looks so clean because a 12th order polynomial was used to remove the noise ripples around the central feature. Now, in that same week, Villanueva et al. Showed that the ALMA calibration procedure was wrong, and that when done correctly, most of the wiggles are gone, including the alleged phosphine line. Now, last month, the original team released their own reanalysis, claiming that there's still a possible much smaller signal left, but that's not seen by other teams. So clearly, the last word is not said about this. I want to mention this here because it teaches us already what a difficult road we have ahead of us. You know, observations of possible biomarker gases in exoplanet atmospheres will always be on the edge of what is technically possible. False alarms will be made, maybe also by me at some point. We're all human. And also a link to real biological activity will always stay very speculative for a long, long time in the future. Okay, moving back to exoplanets. So I want to focus now on observing exoplanet atmospheres. Although we know now of thousands of planets, almost all of them have been found without identifying a single photon from the planets themselves. Now, when you want to do atmospheric measurements, you no longer can do that. You need to separate out the planet light from that of the stars. Well, there are basically 2 families of methods to actually do this. One are the time differential methods. This the actual appearance of the planet changes as function of time in the case of transits, eclipses, and phase curves. And the second are angular differential methods. So spatially or angularly separating the planet light from that of the star. That's basically direct imaging. Now, both these methods work the easiest for warm planets. For transits, these are hot Jupiters. And for direct imaging, these are very young gas giants, still hot from their formation. And both methods have already been very successful with many measurements of different molecules, atoms, ions, temperature pressure profiles from day to night side, evidence for exospheric loss, Rayleigh scattering from hazes, evidence for clouds, the mean particle density or the mean particle mass of the atmosphere through the atmospheric scale height, but also global circulation patterns, direct measurements of winds and planet spin. Now, like all of us, we are eagerly awaiting the launch of the James Webb, which will really be very powerful for these time differential measurements, the transits, eclipses, and phase curves. I really think it will move the field firmly forward. Away from the hot Jupiters we're doing now to much cooler and smaller planets, the Neptune, super Earth, and maybe even a little bit beyond that. This is something I really like about our field. Richard already said, this field is moving very quickly, but it is really moving very quickly. Now, with the James Webb, we can already start to find out whether, for example, the TRAPPIST-1 planets have an atmosphere or not, and whether it's, for example, CO2 based. This is only 5 or 6 years after the discovery of the system. We can already think about measuring such properties. On the bottom left here, you can see models of the brightness temperature as function of wavelengths in the regime of the MIRI instrument, and how different levels of atmospheric mass will actually result in different levels of day to night side heat circulation, and which you can then measure with only a few eclipses. And then also by combining these brightness temperatures at 12 and 15 micron, one can actually identify CO2 absorption or not. I think this is really exciting, and these are type of observations that will already be done very early on as part of MIRI, the MIRI guaranteed time observations. On the bottom right, you can already see something that has been done now. These are observations from Spitzer, led by Laura Kreitberg, who's now a Max Planck director in Heidelberg. This is a planet. It has only an 11-hour orbit around the nearby late M dwarf. It's very hot on its day side, but actually found to be so cold on its night side that it's very unlikely that it has an atmosphere at all. And that is actually something that is expected from models. Now, of course, the James Webb will be orders of magnitude better than what Spitzer has been doing. And so, the MIRI team will actually do this type of observations for the actual TRAPPIST planets, which are significantly cooler. And we will find out to what extent they have an atmosphere or not. Now, in the case of ground-based observations, these families of measurements or methods are combined very nicely with spectroscopic observations of spectroscopic information. The fact that the planets have different spectral features than the star, either due to Doppler shifts or due to other molecular features, it really helps to separate out the planet light from the star, and also from possible Earth atmospheric interferences. Now, these are methods that we have developed and refined over the last decade in my group in Leiden. And we really use very high dispersion spectroscopic observations at the resolution of 100,000, probing the tens or hundreds of individual lines of molecular bands. Now, due to strong Doppler effects, due to the orbital motion of the planets, for the Earth this is about 30 kilometers per second, but for hot Jupiters this can be up to 150 kilometers per second or even more. even during only a few hours of observations, the planet lines move through the spectrum because of the change in Doppler effect, allowing one to separate out them from the non-moving telluric and stellar lines that can be actually orders of magnitude stronger. Now on this slide, you can actually see some of our earlier results on CO, both in transmission and emission. But regarding the time, I actually want to jump to some really exciting recent results from other groups. Here's, for example, on the left in orange, you can see measurements led by the Amsterdam group using HARPS North on the TNG. So this is only a 3.6 meter telescope. This is probing dayside emission from Kelt 9. Now this is Kelt 9 is an amazingly hot planet. There's 4,000 Kelvin or so. It's hotter than most stars in the Milky Way. You can see in the top left panel, if you squeeze your eyes a bit, a curved trail of emission. Actually, the middle panel shows a model of it. This planet is actually so hot that it glows in iron. Now, this is not a place you want to visit. On the right side, you see results from a Nature paper from last year, led by the Geneva group, using the new Espresso spectrograph on the VLT. And these are observations made during a transit, again, of iron, but then of a different hot Jupiter, not so hot as Kelt 9. It's WASP 76b. And yellow here is the iron absorption, with on the vertical axis is time, and on the horizontal axis is velocity in the rest frame of the planet. And yeah, the iron here you see a little bit in yellow, orange. So hence, in the beginning of the transit, on the bottom, we see a little bit of blue shift, which actually rapidly increases to about 15 kilometers per second at the end of the transit. This is 50,000 kilometers per hour. It's quite amazing. And they have a very nice idea of what we're actually seeing here. So why do we see this change in velocity during the actual transit? Now, during the transit, the orientation when the planet is moving across the star, along the star, the planet actually swings a little bit back and forwards, meaning that at different times during the transits we see different parts of the morning and the evening regions of the planet atmosphere. And they show that these observations are actually well explained by there being no iron in the region just before sunrise, meaning because we have strong iron absorption on the evening side, that actually during the night the iron rains out. So I think this is quite amazing, that we can start to find out what the weather is like on a world several hundred light years away. Now, one reason why this method works so well from the ground is that it makes use of a double differential methods, differential in time and differential in wavelength. And this really makes this actually a game of photons. We need more photons, so we need a bigger telescope. Yeah, this is why we get so excited by the ELTs. METIS is a first light instrument with a resolution of 100,000 in an optical field unit between 3 and 5 microns. And high-res will be a second generation spectrograph in the optical and near infrared. And really, if you think about it, both will be able to do mouth-watering things. For transit observations, yeah, the larger telescope directly translate into a significant increase in signal to noise. An example here in green on the left, we can start observing and modeling planet spectra on the day side, morning, evening side, and even the night side, as if these are stellar spectra with detailed information on temperature pressure profiles, abundances, but also wind circulation. We can also start to measure isotope ratios in planet atmospheres. You can see that in the center here, as this is actually a new we think is a new probe of planet formation processes, but also possible atmospheric losses. In particular here, the HDO over water ratio is very interesting. And actually we modeled this, and if Proxima b has water, we could already probe HDO with METIS. So this will be a very exciting thing to actually do. At the moment, we are working very hard in my group to apply such observations for the first time to hot Jupiter, see what isotope of which molecules we can start to measure now already. I had actually hoped to show you this already. We have a very exciting result coming up, but we're battling with nature still, so you have to wait for that a little bit. In the orange pinkish circle here on the right, you can maybe see the ultimate science case. Can we detect molecular oxygen in the atmosphere of an Earth-like planet transiting a nearby late M dwarf, for example, one of the TRAPPIST-1 planets? Now, this will certainly be very challenging, possibly needing several dozens of nights of observing time, several dozens of transits. And then you have to realize, okay, maybe they transit once a week or once 2 weeks, but the star has to be up while the sun is down, while the actual transit happens. So it's only one transit per few months, a few transits a year. So if you need a few dozen of those, you quickly are a decade before you have actually finished such a project. So measuring oxygen in this way, molecular oxygen, I think we'll be pushing it, and we have to be very lucky in getting the right target to be able to do that. However, there is actually another way of probing atmospheres that is extremely exciting, and that is combining high dispersion spectroscopy with direct imaging. Now, this is an idea that has been around for quite a while now, being invented and reinvented several times under different names. In blue here on the left, I try to actually explain this now. So in the blue on the left here, you see a typical direct image of a planet at the bottom of the star here, below the star here. And this is, in this case, clearly identified in the direct image as a planet, but it's still quite far from the host star. What you would really like to know is whether there are any planets much closer to the host star. But this is difficult because there are all these smudges, these quasi-static speckles. And from the image itself, there's actually no way to find out what is a speckle or what is actually starlight, or what is a speckle of starlight, or what could be an actual planet. However, if we now have detailed spectral information, we could actually clearly separate a planet from starlight, because the spectrum of the planet will be very different, for example, because it has all kind of molecular features. Now, let me show this further here on the right. This is actually a white light image of Beta Pictoris. This is a very famous exoplanet system. One does not see the planet in this image because it's actually somewhere on the bottom right. That's because the image is completely swamped by starlight. However, these are data from Symphony. There's an integral field spectrograph, meaning that actually for each pixel we have a spectrum with a resolving power of 4000. And we can actually remove the star spectrum from each pixel very accurately, because it should be everywhere, the star spectrum should be everywhere the same across the image. And then with the residual, we cross-correlate each pixel with a model planet spectrum to see whether there is anywhere any planet spectrum visible. And then with a bit of magic, the starlight is gone everywhere, and we see a very strong signal from the planet, and now at a final contrast of about 100,000 or so. Here you see an example where this technique worked very well. It is again on the Beta Pictoris b planet, but now at very much higher spectral resolution, not at 5,000, but at 100,000. Of course, we don't have yet an RS 100,000 spectral resolving power integral field unit. But if you know, when you know where the planet is, we can actually just put a slit on the planet and the star and do the same trick. So that's what we did here with the CRIRES spectrograph on the VLT. The middle panel shows the result after removing the star spectrum from each position on the slit as well as possible, and then cross-correlating the result with a carbon monoxide model spectrum. Yeah, on the vertical axis here is the position along the slit, with the star and planet position indicated with the dashed lines. And the horizontal axis is the radial velocity in the exostellar rest frame. White is the signal here. And yeah, at the slit position of the star, we see nothing, of course. But at the known planet position, yeah, we see a clear signal. First of all, it's blue shifted by about 15 kilometers per second. This is due to the orbital motion of the planet around the star. It is in about a 21-year orbit. And it's also significantly broadened. And we think that's due to the spin rotation of the planet of about 25 kilometers per second. Because we know the radius of the planet, we have an estimate, this corresponds to a length of day of about 8 hours. Now, this is somewhat faster than Jupiter, that rotates in about 9.5 hours. But actually, this equatorial rotation velocity of Beta Pictoris b is much higher than that of Jupiter. That's because its radius is also 65% larger than that of Jupiter. Now, in the future, these kind of observations may teach us something more about how planets acquire spin while they actually accrete matter. Sorry, I have to get a sip of my drink, otherwise my voice is going to be lost. Now, another, I think, really exciting result more recently is that on the PDS-70 system. Now, this is a low mass T Tauri star with a disk. It's and it is the first protoplanetary disk system with a measured planet, PDS-70b. Probably a few times more massive than Jupiter. You can see it here, just below the star, still inside the ring of dust and gas. There was also some evidence for H-alpha emission for this planet, indicating that the planet or protoplanet is still actually accreting matter. And now Sebastian Haffert, then still a PhD student in our group, but now a Hubble Fellow in Arizona, he came up with this great idea. There's a new integral field spectrograph called MUSE in the red optical. Why not try to use that using similar method as we have shown earlier to get a measurement of this H-alpha emission? So yeah, he went on. He sneakily got the actual observing time because it was only an hour or so. This is the white light image of MUSE. We can tease away the starlight in each spectral pixel again in the same way as we did before, and see whether there's any residual H-alpha emission in the system. And then what we saw was a big surprise, because not only did we see H-alpha at the expected planet position, but we saw a second object. On the west side, there's actually a second planet, PDS-70c. And going back to the archival direct imaging data, indeed, it showed that there is a weak second point source there. So now we have a protoplanetary disk system with not one, but two still forming planets. And again, things are moving very fast in this field. This is a very exciting new measurement with the gravity instrument using VLTI, giving a low resolution spectrum of the new PDS-70c protoplanet, but also constraining the orbits of the two planets very accurately. You know, look at the error bars on the right here. They are at the level of a few hundred micro arc seconds. This is really exciting stuff. So I think if you're looking for new speakers to give an exo seminar, I would invite someone from this exo gravity team. They're really doing some amazing, really groundbreaking work. Now going back to combining high dispersion spectroscopy with high contrast imaging, you have to realize that all these observations that have been done so far have all been done with existing instrumentation. this is, of course, it's far from optimal. You know, for example, Muse has only a very modest adaptive optics system, and the spectral resolving power is only 3,000 or so. We want to combine extreme adaptive optics with a resolving power of about 100,000 or so. Now, there are many projects underway in the world that are trying to actually achieve that. Christoph Lovis from Geneva showed this in a very nice paper, that if you would push an upgraded sphere to its limit and feed it to a high resolution spectrograph like Espresso, you could actually detect reflected light from Proxima b in about 30 nights. This is, of course, pushing it very, very much. This is highly uncertain, this is very difficult, but it does show you the potential of this method. He's actually now working on a standalone instrument because that's actually easier to do. It's called Strato to actually achieve this goal. And almost now every large telescope in the world has a similar instrument project going on, like on Subaru, Magellan, and Keck. But yeah, in my eyes, the real game changer will be MATIS on the European ELT. As already mentioned, it will be one of the 3 first light instruments. It has a integral field unit with a resolution of 100,000 between 3 and 5 microns. This is really perfect and really designed for this type of observations. As an example here, for our nearest neighbor, Proxima b, we expect to be able to measure, if it is actually present, of course, water, methane, CO2, and even isotopologues like HDO. With high res, so this is a 2nd generation ELT, we could take this to the optical and the infrared and target reflected light and molecular oxygen. Note that I mentioned earlier that it would take about 30 nights on the VLT, really pushing it. You have to realize that these type of observations, they actually scale with the telescope diameter to the 4th power. So that's a factor of a few hundred to the ELT. So actually, I almost start to think sometimes that this should be really easy. But of course, this is not the case. Adaptive optics on the ELT, in the infrared and in the red optical will be extremely challenging. I think absolutely it will be doable and will be very exciting. But ultimately, of course, we want to do this as well as possible for the ELTs with extreme adaptive optics at short wavelengths. This will be very challenging and will take probably much longer time to actually achieve, but with very high rewards. Now it will enable these type of observations for not only Proxima b, but probably a small set of Earth-like planets in the habitable zones of nearby late. And with this one slide, which is a much more distant outlook, at least 15 years or now, or two decades. What about true Earth analogs around sun-like stars, for example, which we are going to find with the HARP-3 project? Now, these most likely, very likely, will be outside the realm of even the ELTs. And we'll need something else. Now, either it's going to be a high contrast imaging space mission, like NASA is now under study with LUVOIR and HABEX, or even an infrared space interferometry. Now, we really hope that ESA can play an active role in this. This all seems very far away, but we need to start now if we want this dream to come true. And this is a little bit why I'm mentioning it here. We are eagerly awaiting the outcome of the ESA Voyage 2050 process. That has all been a little bit obscure. I don't know exactly what's happening, but last thing I heard on the grapevine that the outcome of that should come very, very soon. Now, I have reached the end, but there's actually one thing I want to mention. Something very different, something new that we have set up. It's called exoplanettalks.org. This is really an idea born out of the current COVID-19 crisis. which made us think about the future of conferences and symposia. Of course, yeah, meetings and visits will always play an important role in our scientific lives. But I think it's not clear, even after the current crisis is over, whether we will go or want to go all the way back to the way it used to be. You know, flying with thousands around the world is not a very good thing to do, not the most green thing to actually do. And I think that any ways we can reduce that load would be really good. Now, many forms of online meetings have been tried this year, I think with varying success. Some good things, but also I've seen limited time, hardly room for questions, awkward time zones, bad sound, and so forth. And also, actually, it has always been quite difficult for young scientists to present their work, but especially now. There are even less thought after slots than there are actually normal. So we are trying something different, and we have set up a web-based scientific presentation platform for the field of extrasolar planets. Anybody registered can upload a talk to the system, for example, when they have published a paper, a thesis, or at any time. And this presentation is then stored in the system with a range of keywords to make the database easily searchable. No, there are no frills, no likes, no numbers of views, and things like that. Anybody in the world can view a presentation until the owner decides he wants to actually remove it again from the Excel database. And the registered scientists, they can also ask questions either publicly or privately via a discussion console. And so that can be done even months after a talk has been uploaded. So we started with this about 6 weeks ago. Already more than 200 exoplanet scientists registered. More than 70 talks have been uploaded. So yeah, if you're interested, have a look around. Because of course this is a kind of pilot, and but also should be easily extended to other fields if we actually want to. So yeah, that's it, and I thank you very much for listening.
Thanks, Ignas. This was a great talk.